Google DeepMind has just unveiled a massive update to AlphaFold, introducing a free proteomics-as-a-service web app that promises to accelerate biological discovery at an unprecedented scale. The headlines suggest this leap in artificial intelligence might be the key to unlocking fully autonomous robotics as well. But there is a fundamental misunderstanding lurking beneath the hype. While predicting protein shapes with atomic precision is a triumph of pattern recognition, it solves a completely different problem than building a robot that can move through the physical world. Today we are going to unpack why solving the biology of folding does not automatically solve the mechanics of motion, and where the critical gap lies between biological intelligence and embodied engineering. The core promise of AlphaFold is undeniable. It has mastered the inverse folding problem with astonishing accuracy. In this challenge, a protein sequence implicitly encodes its own stable structure, allowing an AI to look at a string of amino acids and predict how it will fold into a three-dimensional shape that minimizes energy. This capability relies on training data consisting of millions of experimentally solved static structures found in the protein databank. These files represent thermodynamic minima points where molecules settle down after all movement has ceased. The model learns to recognize geometric patterns within these stable, resting states with near-perfect fidelity. However, this success creates a dangerous illusion for those hoping it translates directly into robotics. A robot does not operate in a state of static equilibrium. It operates through constant motion, collision, and interaction with an environment that resists change. The leap from predicting a folded protein to controlling a robotic arm requires solving the forward dynamics problem. In this scenario, physical laws such as friction, material fatigue, inertia, and actuation limits must be explicitly simulated rather than predicted from static data patterns. AlphaFold is designed for biological discovery where the target structure is fixed by evolution. It offers no mechanism to account for the dynamic interactions of materials that define real-world movement. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This distinction becomes stark when we examine what happens during actual robotic manipulation. When a robot grasps an object, pushes against a surface, or balances on two legs, it encounters non-equilibrium states and high-energy transient moments where forces are in flux. The training data for AlphaFold consists entirely of static snapshots that represent the end result of folding processes completed long ago. Consequently, the model is blind to the collision dynamics essential for robotic movement. It cannot predict how a gripper will slip on a wet surface, or how an actuator will deform under sudden load, because those phenomena are not encoded in the sequence-to-structure mapping it was trained to perform. Optimization efforts like FastFold further clarify this limitation by demonstrating that AlphaFold's primary bottleneck is computational throughput for static inference, not a lack of physical modeling capabilities. These updates focus exclusively on reducing training time and memory costs to allow more structures to be processed faster. This confirms the architecture is fundamentally a pattern-matching engine for geometry, rather than a physics engine capable of simulating material stress or contact forces. The speed at which we can predict protein shapes does not correlate with our ability to simulate how those shapes might behave if they were made out of metal, plastic, or carbon fiber under load. The gap between biological intelligence and embodied engineering is therefore structural. Biological systems are self-assembling through chemical bonds that inherently account for the local physics of their environment at a molecular scale. A protein folds because it must. Its shape is dictated by thermodynamic stability in an aqueous solution. In contrast, a robot must be built to withstand external forces while actively manipulating those same forces. The materials used in robotics have friction coefficients, yield strengths, and damping properties that vary with temperature, wear, and surface conditions. These variables are not static constants hidden within a sequence of letters. They are complex, time-dependent interactions that require continuous sensing and control loops far beyond the scope of a model trained on static databases. Furthermore, while some discussions online highlight hardware incompatibilities or database implementation bugs regarding these new tools, these are merely technical friction points for software deployment rather than fundamental theoretical barriers to robotics. The real barrier is conceptual. We cannot simply swap biological data for mechanical constraints and expect the same AI architecture to yield functional movement. A robot that can fold a protein in simulation does not know how to pick up a fragile egg without crushing it, nor does it understand how to walk across uneven terrain where gravity acts differently than on a flat plane. The current state of affairs suggests that while AlphaFold excels at predicting molecular shapes with atomic-level accuracy, the leap to building functional robots requires entirely different architectures capable of modeling physics in real time. We are looking at two distinct domains, one dealing with static stability and sequence-to-structure mapping, and another dealing with dynamic instability and force feedback control. Bridging this gap will not come from updating a protein folding model, but from developing new AI systems that can simulate the messy, unpredictable reality of physical interaction. Until then, we must separate the biological revolution in structural biology from the engineering challenges of building machines that move. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.